Oh, by the way, when I accepted you,
Uh-huh.
you were able to access the video, right?
I haven't.
Oh, by the way, when I accepted you,
Uh-huh.
you were able to access the video, right?
I haven't checked it, but I think so, yes. Because before I didn't have access. I haven't
Yeah,
logged
yeah,
in
yeah.
yet.
Because it was not. So there is a button to hit, which is to grant access to all the King's College people,
Oh,
and
okay.
I did that. And hopefully, would you mind checking right now? Is it difficult or is too much time?
It's a little bit annoying
Okay,
because I need to log
okay. So you
out
try to do
from
it. You'll
Nottingham and
try to
then
do
log
it.
in on Kings.
You'll try to do it at some point. All right.
Okay, yeah,
Okay.
it's fine.
Oh, by the way, when I accepted you,
Uh-huh.
you were able to access the video, right?
I haven't checked it, but I think so, yes. Because before I didn't have access. I haven't
Yeah,
logged
yeah,
in
yeah.
yet.
Because it was not. So there is a button to hit, which is to grant access to all the King's College people,
Oh, okay.
and I did that. And hopefully, would you mind checking right now? Is it difficult or is too much time?
It's a little bit annoying
Okay,
because I need to log
okay. So you
out
try to do
from
it. You'll
Nottingham and
try to
then
do
log
it.
in on Kings.
You'll try to do it at some point. All right.
Okay, yeah,
Okay.
yeah, it's fine.
So clusters.
Mm-hmm.
Uh, just as a concept, yeah. It used to be the only concept possible, the only model possible. So you have a crystal. For example, let's start from a surface. So you have a surface of a crystal, yeah, something like that. Okay, so it continues in all directions, and here, yes, but not up. It's not. Oops. It is not going up. This is a surface. We terminate it here. And with and a simple model would be simply to cut out that thing. Say, take this bit, yeah, and remove all this stuff. So what you end up with is a finite fragment. In this case, with 9 atoms, but this is just kind of model, and there's nothing you should do here. However, the question is, what do you have to do here? Because there used to be atoms there, and now there's nothing. So that model is very, very approximate. So what people do sometimes in covalent systems, what they do, they look at what kind of bonds you have here between atoms. For instance, you cut it in such a way that there's a single bond. Yeah. For example, in the case of silicon, you can do this, because silicon has directional bonds between atoms. And there is always a way to choose a fragment in such a way that every atom on the surface of the fragment, would be connected with a single bond with its neighbor, which is not included in the cluster, outside the cluster.
Mm-hmm.
In that case, what you can do, you can hang a hydrogen atom here. Yeah. It's a kind of a simple concept. This hydrogen atom is used as, so the concept is called a linked atom, link atom. So you link that atom of your, at the boundary of your cluster with something which can donate an electron and accept an electron in some sense. And, oh, just 1 second. Алло. Алло, Владка, говори, у меня сейчас лекция. С тобой все нормально? Да, у Ники вроде тоже все нормально. Мы ждем, может, они сегодня приедут. Потом мы с тобой поговорим, да? Пока. Bye. So and the idea is to try to minimize as much as possible the effect of this cutting the cluster. And if you put these hydrogens there, um, they would donate an electron and would be able to establish a covalent bonding with the boundary atoms of the cluster. And this way, the effect of cutting would be actually minimized, right? In actual calculation, you can keep the cluster geometry as it was in a periodic system and only relax positions of these hydrogens, because if hydrogens, of course, hydrogens do not replace the actual atom of the crystal, which would stand there, but you can move these hydrogens a little bit so that the system would not be strained. Okay, so you would keep the positions of the atoms of the cluster fixed. You would only move hydrogens, minimize the energy, and then when you do the calculation on your system, you would probably you would most likely fix the hydrogens at these positions and allow atoms of the cluster to move. Although if you can do this, if your computational power allows you to doing that, you can fix the positions of the boundary atoms as well, which would be a good idea. However, that would require for you to have a lot of atoms, enough atoms inside the cluster. So this makes a cluster large. So the cluster, what is the advantages of using clusters? If you use a cluster, you have access to high quality quantum chemistry methods, which can take account of electron correlation effects quite well. However, these methods are quite limited in their power because they're not very efficient. They scale very badly with the number of atoms in the system. We're talking about the n to the power of 7, 9, depending on the 5 maybe, depending on the quality of the method. All right. So clusters in that sense are good because you can actually put something on top of the cluster. So let me minimize. You can put something on top of the cluster, some molecule or whatever, yeah, and you can study interaction of that molecule with the surface of your crystal, and use quite sophisticated methods. However, you should remember, as I said, these methods scale very badly, so you can't really afford doing a very large cluster and a very large molecule on top. And you have this boundary effect. So it's never clear what is the main contribution to your error. Yes?
I just had a question with the boundary effects. Is there an implementation that you use periodic boundary conditions?
No. In that implementation, we do not use periodic boundary condition.
Okay.
That's the concept of the cluster. Sorry, I didn't mention that. That's the whole idea. You do not use periodic boundary conditions.
Okay.
Although you may use periodic boundary conditions and start kind of periodically repeating this thing with the largest vectors, so they would not interact. Yeah.
Okay.
You can do this, but then you will have to use DFT in all these periodic codes, and then all the whole point would be completely lost. Yes.
Okay.
We will come to this. Yeah. So the point here is that we can use quantum chemistry methods, which are not based on periodic boundary conditions, and therefore you have access to some more sophisticated methods which go quite well beyond DFT and are very you can systematically improve them to approach the inaccuracy, the exact results. But then there is this dilemma, whether this would worth it, because you would destroy your crystal by taking a fragment and replacing the missing part with these hydrogens, and it's not quite clear how big an error you're making. So that is quite questionable, yes. But in some cases, for instance, we come across this actually with my collaborators. we did calculations with DFT, and the results were quite strange. It was gold atom on a silver surface, and on top you have a CO molecule. And CO molecule, according to experiment, CO molecule wanted to be have been seen next to the gold atom adsorbed on silver. However, the calculations never show that. Calculations show that if you put a CO molecule either way, either with carbon or oxygen down next to the gold, it actually climbs on gold and forms a chain. Yeah, so DFT calculations show that, and we tried hybrid functionals, we tried different things, and the conclusion was DFT always showed that. So the question was, maybe this is because, you know, DFT is simply not doing the right job, the good job. So then the guy in Slovakia, he cut off a cluster and used couple cluster method. This is one of the methods available for finite systems, which goes beyond DFT, but it's quite expensive. But still, if you really need to do this, and he managed to reproduce this result, which means that in spite of these boundary effects, so you see, you don't have an ideal solution. In DFT, you don't have boundary effects, right? But you don't have the exact method. In cluster approach, you do have an exact method, or at least you can systematically approach the exact method, but you don't have the right model. So this is what we have. That's what we have to live with. Okay, so this is the cluster approach. You just need to be aware that this thing exists. It has its own advantages and disadvantages, and but this is one of the possibilities, at least, so to have in mind. So in that case, you have a finite system, which you cut out of a 3D system. You may terminate with some something, with some link atoms to what's the word, to saturate the bonds of these atoms at the boundary, to minimize the effect of the boundary, and then use high quality quantum chemistry methods to study something you're interested in, but this is not always possible. So we need to use periodic codes, DFT. Yeah, if we use DFT as another alternative, we can't go beyond DFT. Although there are codes nowadays which go beyond DFT and still use periodic boundary conditions. For example, GW codes, but they're very, very expensive, and we're not going to discuss them. But you may still, you know, think that there are things better than DFT. Yes, there. Yeah, with their own kind of problems and efficiency issues. It's not yet as widely accepted as DFT. DFT became really a working horse right now. But there are other methods as well. All right, so in order to run a DFT calculation, you need to set up the periodic cell. Yeah, and that periodic cell may not necessarily be a primitive cell of the underlying crystal. Yeah, because you would like to put a molecule on top. You would like to consider, say, interface between two different crystals. So your cell, which you periodically repeat, would be much larger in most cases than the actual primitive cell of any ingredient crystal. And that means that we have to consider the geometrical issues which are involved here. Yes. So let's start from a simple periodic crystal. And here I can indicate lattice vectors. Yeah, these are primitive lattice vectors. I can call them A1 and A2. Don't ask me to draw in 3D. I can't, but
Okay.
that would be enough. I hope, yes.
Uh-huh.
So these are primitive lattice vectors, and applying these primitive lattice vectors, you can reach any, in all possible linear combinations, you can reach any lattice point. Yeah, so from this lattice point here, you can reach this one, of course, this one, and also this one. This will be the sum of the two, and this one, and this one, and this one. So basically, what you're doing, you're writing a lattice vector as a linear combination of these primitive translations. And these two are integer coefficients, which could be 0, plus minus 1, plus minus 2, anything. And by running all possible values of these coefficients, you can construct a vector L, which would connect your initial point, this one, with any other point of your crystal. For instance, if I want to connect this point and this point, what I need to do, I need to go 3 times with A1 and 2 times with A2. So this particular vector would have the following structure. It would have 3A1 plus 2A2. Yeah? So you can reach any point on your lattice. Right? So if we were initially in that 0 cell, with that lattice vector, we are here in that cell. Yeah? And by changing these integers, you can reach any cell. All right. The choice of these primitive lattice vectors is not unique. You can take them in some other way. For instance, instead of this choice, I can do this. I can take this, the A1 the same, but A2 I can take this one.
Yes.
Or I can take A2 this one. Or yeah, or this one. Yeah, so you have quite a choice. The only condition you need to think about and satisfy is that the volume of that cell you construct is the minimum possible. Yeah. So if you have 3 lattice vectors A1, A2, A3 that form that kind of a parallelepiped. Yeah. So this will be the volume of that unit cell can be obtained by a triple product of these 3 vectors. Do you know what triple product is? You do a vector product here, and then the dot product with this. Yeah. You can also write this triple product as a determinant. So you run all 3 components of vector A1 along the first row, then vector A2 along the second, vector A3 along the third. So that would be the determinant giving you this value. Okay, so this is the primitive unit cell. This is the smallest cell. There are some other choices of the cell. You may have heard of Wigner cell, but these are all different kind of choices. How would you choose in the periodic crystal a volume which would, if periodically repeated, reproduce the whole thing? And that not necessarily of a parallelepiped shape. It could be of other shapes. A Wigner cell is kind of a sphere-like, yeah? And you can also cut out something like that. Or it won't be like that. It would be something like that, yeah? So that it would periodically repeat it and you reproduce the whole thing. But for us, that kind of cell, parallelepiped-like, is what we want. Because with the Wigner cell, it is not easy to represent it simply by vectors.
Okay.
So the choice of the primitive cell is not unique. And what we want to construct large cells. We call them supercells as well. And this can be done by simply constructing 3 non-complanar vectors L by choosing these integer coefficients. Non-complanar, which means that they must not be within the same plane. So they would make a volume. Yeah. So you may take, say, one vector. Let me have blue color. You can have one vector, say, like this, another vector, say, like that. So your cell then would be like that. Yeah. So
Yes.
your new vectors will be a1, which is 2 times a little a1, and a2 will be, what will it be? Let's see. Uh, so we go 2 negative along a1
And
and 2
two.
positive along a2. Yes, in this
Mhm.
example. So there will be minus 2a1 plus 2a2. That relationship can be written as in the form of a matrix. So I can write that AI, my vector AI, is the sum from 1 to 3 with some coefficients t, and here little vector a. And in my example here, that matrix T has a very simple form. It has 2 here on the one at the 1, 1 position, 0 here, then minus 2 here and 2 here. This is my matrix. Yeah. So if I write here A1, A2, and multiply, I will get A1 vector, A2 vector. Yeah.
Yep.
In 3D, this will be a 3 by 3 matrix. But apart from that, it's exactly the same concept.
Yep.
You may want sometimes to build a cell which is of a certain shape you fancy specifically for this or another reason. Let me show you on an example how this can be done. Okay.
Okay.
Um, so let's consider an FCC crystal. It's a cubic crystal, face-centered.
Mm-hmm.
For that crystal, the largest vectors of the primitive largest can be written in the following way. So now we will have a little mathematical exercise, but I think we will have to do this kind of exercises from time to time.
Good.
So this would be 0, 1, 1. Oh, sorry, 1, 0, 1, and A3 is A over 2, 1, 1, 0. So the A here, the little a, is a lattice constant. And if you draw these 3 vectors, they form a kind of a bent parallelepiped, something like that.
Mm-hmm.
You may want to construct instead a cell in which these lattice vectors capital A are perpendicular to each other. Yes?
Yes.
So you would like, and this is called crystallographic cell.
Yes.
A crystallographic cell is the smallest possible cell of a cubic shape. It is not the largest cell. It is not the smallest cell. The smallest cell is this one, this parallelepiped. This is smallest possible volume you can construct, repetition of which would reproduce the whole infinite crystal. If you construct a bigger cell, it will also be able to reproduce the whole big crystal. However, it will be bigger.
Yes.
Yeah. All right. But for us, we would like to do a new cell. So we write 3 equations. So A1 is N1 A1 plus N2 A2 plus N3 A3. I can't write. It's very cold here, I should say, and they have so they rebuild the building,
Okay.
and there's a kitchen which is empty to the whole world.
Okay.
So you can imagine the temperature here is about 2 degrees.
Mm-hmm.
So these 2 degrees, they penetrate the whole house because we close
Where are
the
you?
kitchen and they're working there, but it's open.
Are you in London?
Huh?
Are you in London?
It's not London. It's the south of London.
Oh, okay, okay, okay. Okay, it's to the UK.
So yeah. So it's very funny, and I have to sit here. Anyway, so you can imagine. So we have this. Yeah. So these coefficients, because the vectors a1 and 2 and 3 have very specific form, I can actually write this like this. So watch me. N1 a over 2 and then 0, 1, 1 plus N2 a over 2 1, 0, 1. So now write them as vectors. So this will be then a over 2. We can take out. Here we'll have N2 plus N3. We have here N1 plus N3 and here N1 plus N2.
Correct.
All right. So this is A1. Yes. A2 would be A over 2. And it will be, so here we need to be a bit careful, but okay, let's use a different notation. So it will be a different, but very similar linear product.
Yes.
Linear combination, but with different coefficients. Remember, we have this matrix T, which should have 9 elements. Yes. In this 3D case. So we have 3 elements here, 3 elements here, and another 3 elements would come from this
A3
vector. Yeah? Let's call them P. P2 plus P3, P1 plus P3, P1 plus P2. So these are all integer coefficients. We would like these vectors to be along XYZ axis and perpendicular.
That'll be great.
Yeah. So we would like A1 have a structure, some constant A, and then 1, 0, 0. A2 is A, 0, 1, 0, and A3 is A, 0, 0, 1. So this is what we want. And we would like to find the coefficients, these 9 coefficients, to accomplish this transformation. And we would like to choose these coefficients such that the obtained cube would be of the smallest size possible, smallest volume possible.
Okay.
All right. So let's go on with that job. Yeah. So let's look at A1 first. According to the structure of A1, we have 3 equations now. So A over 2 N1 plus N3 should be equal to the capital A. A over 2 N1 plus N3 should be equal to 0. A over 2 N1 plus N2 should be equal to 0.
Yes.
Yes?
Yes.
So from the second equation, we get that N1 is minus N3. From the third equation, we get N1 is minus N2. So N2 and N3 must be the same and equal to minus N1. So from the first equation, then, we have N1 twice equal to A over little a. So N3 is minus N1. Oh, wait. No, I made a mistake. Sorry, I made a mistake. It's here N2 plus N3. Yes, N2 plus N3. So that will be then. Let me correct myself. N2 plus N3, but N2 and N3 from these 2 equations are the same. So we have A over 2, 2 times N2 equal capital A, or N2 is capital A divided by the small a.
Yes.
So this is N2, N3 is the same, and N1 is the opposite of these 2.
Correct.
So we have found now 3 these expansion coefficients in that expansion here, A1. So they seems to be A over A, and the first one is minus 1, the second one is plus 1, the third one is plus 1. Obviously, for other two cases, for other two vectors, you will have something similar. But the -1 would appear on the second position for the A2 and the third position for the A3.
A3, yeah.
Yeah. So my transformation matrix now we can write. So this A1 goes to here. A2 would have a similar form, but with -1 in the middle. And A3 would be similar form, but a -1 at the end. So the matrix T we have would have the following structure.
Okay, so we grabbed.
Q.
Ah,
So that's my
yeah,
matrix
sure.
T. That's my matrix T. You see?
Mhm.
So that matrix, if you apply it to any of the vectors, would make them along the directed along the Cartesian axis,
Okay.
and therefore they will be perpendicular to each other and of the same length.
Mhm.
That's what we want. But we would like them to be of smallest possible volume. Let's calculate the volume. The volume, capital VC, as opposite to the small VC, which would be my primitive unit cell volume, yes,
Mhm.
would also be given by this mixed product. So I will have to construct determinant like this and calculate it. Okay, let's do it. So that would be -1 times 1 minus 1 minus 1 minus 1 minus 1 minus 1 plus 1 1 plus 1. So it will be a over a cubed. And here, so this is 0, this would be 2 and 2, 4. 4. The volume of the primitive cell, VC, little one, will be given by a over 2 cubed. And here we have 0, 1, 1, 1, 0, 1, 1, 1, 0. This is constructed from these primitive vectors.
Mm-hmm.
And that will be equal to, let's see, a over 2 cubed. And here we have minus 1 minus 1 plus 1, 1. So it will be 2. So 2a over 2 cubed. So the ratio between the two, now we can calculate it. A over a cubed 4 divided by a over 2 cubed 2. It will be 2 times. My brain is not working.
So that's 2 times 8, so 16, right?
Something is wrong here. Something is definitely wrong.
Let me check the determinant. -1.
I forgot something. I must have forgotten something. Let me see. A. So A, this capital A should be in units of length. Of course, I've forgotten this A. There must be A in front because we still have to, yeah. So this A, so there will be a cubed here as well, which we've forgotten. And therefore, there will be another a cubed here, a cubed here, a cubed here. Now we should be good. So there's an additional a cube here. So we have a in the power of 6 and little a also in the power of 6. Now we have the right dimension. And 2 from here went into 8 over there, and 2 of these 2 gave me 2. So we have 8, so we have 16 a over a in the power of 6, apparently. But the point is, we need to make the smallest possible volume. How can I make the smallest possible volume? I need to choose this capital A, because we haven't chosen this yet. So how would I achieve the smallest possible volume? What choice of capital A would give me the smallest possible volume?
So
it should be in units of little a, because otherwise the whole thing, because you see these ends, they should be integers, and these ends are this ratio, so that ratio must be integer.
Correct.
We can have it either 0, 1, -1, 2, -2, etc., right?
Yeah. Okay. Yeah.
You can't choose it 0, because then way all luck is 0.
Yes.
So the first possible choice is capital A over little a is 1. Yeah, so we choose capital A equal A, and our volume then. I have an impression that that is wrong, but because it should be 4 in my view. I quite don't understand why this. Anyway,
I'll
you can
check later. Don't worry.
yourself. You can check the algebra yourself. But the point is, the smallest possible volume is achieved with this little a, capital A.
Okay.
And therefore, our vectors, now we can write the vectors. Now our transformation matrix T, this one, with the A over A equal 1, with the A over A equal 1 and capital A equal little a, becomes, so wait, now I think I know where I made a mistake. When writing this transformation matrix, so there is no mistake here. So here, it is correct. But the transformation matrix contains the little vectors A as well. So this is not wrong. This is not right. So this is not right. But the idea of the transformation matrix is correct.
Okay.
Yeah. So our new vectors are here. So this is not quite right. But so the prefactor. Okay. So let me remove the prefactors, because the prefactors are wrong, but the matrix is correct. The type of, so there's a factor is missing. You can easily reinstate the factor, because the vectors are correct. So the vectors are then A1 is A minus 1, 1, 1. A2 is A 1 minus 1, 1. And A3, oh, wait a second. No. I'm doing something rubbishy. So the vector A1 is, so now we're rewriting this. We're writing this. With these values of the coefficients. Okay. So all these coefficients are equal to 1 or minus 1. Yes, because capital A is the same as little a.
Yes. Yeah.
So so for example, A1 is A over 2. And here we have n2 plus n3. n2 and 3 are equal to 1. So this will be 2. And 1 plus n3 is 0, 0. So it will be A, 1, 0, 0. This is what we wanted. At the same time, we need to know what kind of linear combination we construct. And the linear combination we construct is this one here. Yeah, with the coefficients given like that. So it will be minus A1 plus A2 plus A3.
Okay.
So actually we have a equal sign here for the transformation matrix. We do have an equal sign. So what I've done here is is a bit wrong, because we got this factor wrong, yes. But now we can see that the transformation matrix which relates capital A and the small a is actually consists of plus and minus ones, as it should. It should consist of integers only. And now we have A2 as A 0, 1, 0, and at the same time A1 minus A2 plus A3. And A3 is A 0, 0, 1, which is A1 plus A2 minus A3. So this is the calculation we have performed. So we have constructed a unit cell which has perpendicular lattice vectors. Yeah, so A1, A2, A3 of the same length and of the minimum possible volume. And the calculation, the construction is performed by this matrix. We have derived this matrix as well. So this is the matrix T, which performs the transformation.
So we had our primitive unit cell that was this weird parallelogram that was a little bit tilted. Yeah. And then we found out this transformation, this linear transformation matrix that basically takes that basis and transforms it into orthogonal ones.
Yes. So we construct a linear combination because in fact, we are free to choose any linear combination we like.
Yeah.
The problem with that is you may or may not have the same volume. In this case, it is not possible to construct the same volume, but the lattice vectors to be perpendicular. Yeah. It will necessarily be so because the smallest volume possible we constructed is with this matrix.
Yes.
And the determinant of that matrix is 4, I think, is 4. So the determinant of that matrix is 4. So capital VC over small vc is 4. So our cell we constructed 4 times bigger than the primitive cell.
Okay.
It is the smallest possible cell of that shape. So it is not possible to construct that shape of smaller volume.
Okay.
Yeah. Of a smaller volume. So this calculation I have performed should have been without these prefactors. And then we would nicely have 4.
4.
Yeah. Okay, so all this rubbish we remove.
Everything's so easier now. So much easier
No,
now.
but did you get the point? Yes.
Yeah.
So how I perform the calculation? So you basically write these equations, then make them equal to whatever you like, and then you simply think what would you do? Yeah, with this.
Okay.
So we accomplished what we wanted. We constructed that matrix T, and if you remember, Theta needs this matrix to construct the new cell. So
it does
this, and with that cell you can construct that now. So now you know how this matrix looks like. So you can construct this orthogonal, not orthogonal, cubic cell, if you want. Yeah.
Yeah. Can I ask a question, Lev?
Yes.
On practical terms, usually what I did so far is I went to the crystallography open database. I copy-pasted a CIF cell file, and I converted it into something that VAS can read. Now, there's 2 space groups of, for example, gold. What are these space groups? What's the difference between the space groups? Is it just the ones orthogonal and the other one is the...
What do you mean 2? Each crystal has 1 space group. There could be several, what they're called, representation. No, representations. In international tables for crystallography, they call them somehow. But some groups have like a view, a different representation.
Okay.
Of some sort, yes. But they're equivalent.
Okay.
If you're talking about the database, I really don't know what they do. Maybe they simply construct you different cells, as we have just discovered. You can have different choices.
I think that's what they do.
Yeah. What is the space group? We can cover this today as well.
Okay.
I can explain this to you rather quickly. So in practical calculations, what would you do? Let's now talk a little bit about bulk and going from the bulk to the surface. Yeah. So suppose you have a crystal with some unit cell vectors, which you can take from this database, primitive unit cell.
Yes.
Then you would need to do a calculation on optimizing the lattice vectors of that lattice. For example, in the cubic cell, you would have to optimize for the FCC lattice that constant A, lattice constant. And you can do it in different ways. You can, for instance, construct the primitive cell and then just change the value of that A in these vectors.
Yes.
And that is probably the best way of doing that, because in this case, you have the smallest number possible of atoms in the cell, which is good for the calculation. The calculation is simple anyway, but at least you will have to specify many key points. We'll have to come to this, though. And you would run the calculation without any relaxation. For example, if you do gold or if you do copper, something like that, yeah, 1 atom per cell. It could be a little bit of a problem if there's an odd number of atoms. You have to use something different. You know.
Why is that a problem if you have an odd number of atoms?
Because then you have a problem with the spin. So it's better because the system is neutral and spin is saturated. So the system has 0 total spin. You would have for each electron spin up, you will have another electron spin down. If you have a primitive cell with an odd number of electrons, you can't achieve this.
Okay. So if I'm, for example, simulating gold, I could just double my cell, put 2 atoms in it.
You can double your cell, but in that case, the cell would be a little bit asymmetric.
Yes.
So it's better in this case to make the crystallographic cell we have just constructed. It is 4 times bigger, so you will have an even number of electrons. And it is the shape of the cell coincides with the point symmetry of the crystal.
Yeah. Okay.
And that is the perfect choice, because the calculation is very simple anyway. So I would argue, this would be the best choice possible in this case.
Okay. Yeah? So in that case, you put the entire FCC in 1 unit cell.
Yes.
So
yes.
8 atoms.
So it would be 4 times bigger than the primitive cell.
Correct.
Yeah?
Okay.
So it will contain 4 atoms instead of 1. Yeah?
Okay.
Right. So you have your cell, which you used to run the crystal. I have to finish. So you would make this crystallographic cell, for instance. The size of the crystal of the cube would be exactly equal to A. Yeah, as we just discovered. Yes. And you would simply change this A, but you have to do it very carefully, because as you change lattice vectors, the positions of atoms in the cell should change appropriately. So in this case, the best choice is to specify atoms in the cell in fractional coordinates, which means that atomic positions, let's call them capital X, would be given as linear combinations of lattice vectors of your cell. In this case, these numbers are not integers. They're between 0 and 1.
Yes.
Between 0 and 1, excluding 1. Because these indicate positions of atoms inside the cell. Yeah. So if you choose in the code atomic positions in Cartesian coordinates, which you can also do, when you change the lattice vectors, you will have to move atoms inside the cell appropriately. Otherwise, for every cell, you will have to relax the system, which is completely beyond the point.
Okay.
If you use the primitive unit cell, then you don't do at all this. Because with the primitive unit cell, you rescale lattice vectors and the whole system rescales appropriately.
Yes.
If you now use 4 atoms in the unit cell, you rescale your cell. Only 1 atom rescales appropriately. All others within the cell, they do not move.
Yes.
So by using fractional coordinates, by specifying these coefficients instead, and in VASP, for instance, you have this option. The code calculates the positions of atoms within the cell by applying this formula. And therefore, as you change these capital A's, capital X's change appropriately. So the whole thing breathes out or in correctly. And you don't need to do anything. You just change the lattice vectors. And in VASP, there's even an option, rescale. You specify a single parameter, a scaling constant, which is the second, I think, on the second line in the postcard file, or maybe the first, no, maybe the second. And it would do this job. But you have to specify lattice vectors. Actually, if you specify lattice vectors in Cartesian, I think it would rescale everything. But I'm not sure how this is exactly implemented. Maybe it will. But I would simply use fractional coordinates.
Okay.
Option fractional coordinates. And this constant P, they would be like 0.25, 0.5, something like that.
Yeah.
Yeah. So they would not change as you rescale the lattice, right? And therefore, if you rescale the lattice, they will move appropriately. So you would calculate the energy of that system, and then plot it as a function of this little a, and would choose the minimum. This, how would you choose the optimum value of the lattice constant? Okay?
Okay.
So suppose you have done this job, and you have constructed your primitive cell. Now you know what this little a is for your lattice. Now you can use primitive lattice vectors. You can go back from the crystallographic unit cell to the primitive unit cell, because this time you would like to construct a model for your surface with the maximum flexibility possible.
Okay.
And if you use crystallographic unit cell, you lose a little bit of flexibility because your brick, elementary brick, is already 4 times bigger than it could have been.
Okay.
Yeah. So so what you do? Let's think. So Tether has an option for that.
Yes.
So, but let me explain you the idea of that option. So this is my surface. Yes.
Yes.
So I'm trying to somehow something like that. You have an idea, yes? I said.
Yeah. It's hard to draw in 3 dimensions.
I hope you have an idea. These are the edges of my little construction.
Yes.
Okay. So our bulk cell would give you an object like this here. Yes? This is our bulk cell.
Yes.
In order to construct a surface, you need to move, you need to make this thing to go parallel along the surface. So you'll have to choose 2 vectors at least, not at least, exactly 2 vectors within the surface. Your vectors, which we use a red color for, these ones, say, they may not be along the surface. They might be, but may not be. So you need to use linear combinations of your vectors, staying within the primitive unit cell volume, but such, because remember, we can do this. We can choose primitive cell vectors in many ways possible. Yeah. So we will find a linear combination such that it would keep the volume the same, but will have two vectors within the surface.
Okay.
How can we do this? So Theta has a facility for that. It starts from constructing the crystallographic unit cell first. Now you know how to do it.
Yes.
At least for FCC.
Mm-hmm.
For cubic crystals, it's very easy to do. And then it uses Miller indices.
Mm-hmm.
Miller indices. So if we want this surface to be, say, 1, 1, 1, that means that so-called reciprocal lattice vector, which I will explain now in a second, must be perpendicular to the surface. Yeah. For that, we need to construct, to be able to construct reciprocal lattice vectors. And then, once we know reciprocal lattice vector, we will know the normal to the surface. So we can then choose linear combinations of our small vectors, such that two of them, say number 1 and number 2, would run within the surface.
Mm-hmm.
Yes?
Yes.
So let's consider this quickly. So reciprocal lattice vectors. So we have a direct lattice, which is specified by these little a vectors. And we can construct a reciprocal lattice, which is specified by small b vectors. And these vectors are related to each other by the following equation. So here I have a dot product of vector ai and bj.
Mm-hmm.
And if I and j are the same, the dot product would give me 2 pi.
Mm-hmm.
If I and j are different, dot product would give me 0. For instance, if I would like to construct vector b1, I would have 3 equations for that. a1 b1 is 2 pi, a2 b1 is 0, a3 b1 is 0.
Okay.
Yes, and the vector, and these 3 equations are sufficient to find the vector b1, because any vector in 3D space contains 3 components, and we have 3 equations to find them.
Mm-hmm.
In fact, you don't need to do this, because there is a known analytical solution to these equations. And I can just write it down. So b1 is 1 over, oh, is it 1? I think 1 or 2 pi. No, maybe 2 pi.
I can check.
2 pi over Vc, A2 over A3. B2 is 2 pi over Vc. Vc is the primitive cell volume. A3 over A1. In B3 is 2 pi over Vc. A1 over A2.
Yes. So, Lev.
Yes.
Where does the 2 pi come from?
Oh, it's just a convention.
Okay.
It's just a convention. So let's calculate these vectors for our FCC lattice as an exercise, yeah?
Mm-hmm.
So let me do it that way first. Remember how vector A1 and A2 are. So we have B1y A over 2 plus B1z A over 2 is 2 pi. So let me just copy and paste this here, because otherwise you will not remember.
Ah, yeah, that.
Okay, so this is our kind of vectors. Then b1x a over 2 plus b1z a over 2 is 0. b1x a over 2 plus b1y, a over 2 is 0 again. So we have then b1x equal minus b1z, b1x equal minus b1y, and therefore z and y components are the same. So will be 2 times b1y, a over 2 is 2 pi, and from this one 2 cancels out, b1y is 2 pi over a, b1x equal, and this is the same as b1z, b1x is minus 2 pi over a. So b1 vector is 2 pi over a minus 1, 1, 1. And you can guess that b2 would be just the minus 1 would move to the second position, b3 to the second position, to the third position. And the same equation, these equations give the same result. Well, let's work this out. 2 pi over vc, then a2 over a3, that would be ijk a over 2, no, a over 2, 0, a over 2, a over 2, a over 2, 0. So that will be 2 pi over vc, I multiplied by minus a over 2 squared, minus j multiplied by, wait, j is this, that, also minus I over 2 squared roots, plus k, I over 2 squared.
I over 2 squared.
So that would be 2 pi over vc, a over 2 squared, minus I plus j plus k. Then vc we worked out before. vc is this.
Yes.
So vc is 2 times a over 2 cubed. So this will be 2 pi 2 times a over 2 cubed, a over 2 squared, then minus 1, 1, 1. And this cancels out. This cancels out. We have nicely 2 pi over a minus 1, 1, 1, exactly the same result. Yeah?
Yes. Yeah.
So you see, you can always construct these reciprocal lattice using this equation. So these are the equations to use. They're valid for any lattice. Cubic, orthorhombic, hexagonal, whatever.
Yep.
For any lattice, these are valid. And now, if you would like to construct a specific surface, say 1, 1, 1 surface, then you need to construct the reciprocal lattice vector 1, 1, 1, which is 1 times b1 plus 1 times b2 plus 1 times b3.
Okay. That's why I'm calculating this.
So if you want to construct so-called HKL reciprocal lattice, where HKL are integers, you would construct this. Yeah? So in our case, we simply need to sum up 3 lattice vectors. Each of them has this 2 pi over a as a prefactor. The first vector is 1, 1, 1. The second vector 1 minus 1, 1. And the third vector is 1, 1 minus 1.
Correct.
Yeah?
Yes. For 1, 1, we have this.
So we would get then 2 pi over a. And here we'll have 1, 1, 1. That's the vector. So if you now draw, so this is direct lattice, yes? So this will be X, Y, and Z. So my first lattice vector is this one.
Correct.
Yes, so it's between Y and Z. So it will be directed something like that. My third lattice vector in the XY plane, so it will be like that. And the third, you can guess, it will be in the XZ plane. Yeah? Their sum will be vectors sticking out of here exactly in diagonal direction.
Yes.
Towards the corner of the cube.
Correct.
Yeah, formed by this. Okay, this is not very good drawing. So my plane will be then perpendicular to that vector.
To that vector. Okay.
Yeah, so this is one plane of this crystal.
Okay.
Okay, so now we worked out G111. But tether doesn't need this vector. For tether, it's just enough to construct this plane. Oh, wait, we made a little mistake, but I think we haven't made a big mistake. But one thing which is confusing, for me, it was at some point, I remember, very confusing because people do not mention this in textbooks. Of course, it's a matter of convention, but nobody noticed that, mentions this convention. The convention is that Miller indices are with respect not to the primitive, but to the crystallographic cell.
Yes.
What we have done in these calculations, we used reciprocal lattice vectors of the primitive cell.
Oh, that. Okay.
We made a mistake, right? What we should have done, we should have used reciprocal lattice vectors of the crystallographic cell. But you will see that we actually, the result is the same, yeah? Because our crystallographic cell is given by, so crystallographic cell is given by these vectors capital A. Remember, and capital A was A, 1, 0, 0, A2 was A, 0, 1, 0, and so on. And if you now work out the reciprocal lattice vectors corresponding, let's call them capital B, corresponding to this lattice, it's very easy to work them out. It would be 2, it would be pi over A, 2 pi over A. 2 pi over A, 1, 0, 0, the same.
Okay.
Multiply, say, this one with A1. It would be 2 pi. Multiply this one with the A2, it will be 0. So that condition is nicely satisfied. So because our crystallographic cell is a primitive or simple cubic lattice, and for a simple cubic lattice, reciprocal lattice is also simple cubic.
Okay.
In fact, for FCC lattice, the reciprocal lattice is BCC. BCC lattice in the direct space is FCC in the reciprocal space. So these lattice vectors of the reciprocal lattice we just obtained, this is a BCC. You can check it in the textbook. -1, 1, 1, 1, minus 1, 1, 1, 1, minus 1. This is BCC. And if you choose these vectors as your real space vectors, you will get these ones for the reciprocal. So they're kind of reciprocal to each other.
Yeah.
Yeah. But the simple cubic lattice is reciprocal to each other, to itself. So B1 is that, B2 is the same, with the 1 in the second position and B3 in the third position. Now let's work out G11 with respect to the crystallographic cell. Again, we'll have to take a sum of these 3 vectors, but the big ones. And you can immediately see it is this. That's the same.
Yep.
Okay?
Yeah.
So that calculation gives the same result, but this is what's called? Would you say a puke?
Fluke.
Coincidence.
A fluke.
A fluke. Fluke. Sorry, fluke.
Yeah.
Coincidence. Yes. Yeah. Of some sort. So this is the correct calculation. This is the correct calculation. Puke is something different.
Yeah. Puke is something different. Yes.
Right. But again, theta doesn't need this.
Yeah, you just need the millimeter.
Requires for you to construct the crystallographic cell first, with respect to which milli-indices would be specified. So once you constructed the extension to the cell, with respect to which the milli-indices are specified, and you need to really research this with respect to what somebody has given these milli-indices. Yeah. Mm-hmm. Once you have done this, you simply specify milli-indices, and theta does the job for you. So theta actually calculates this reciprocal lattice vector, capital G. Mm-hmm. So it knows the direction of the normal. It doesn't need this prefactor 2 pi over a. It just needs the direction. Yep. And then it works out a linear combination of the small a vectors such that 2 of them would be perpendicular to that direction. So, which means they would be within the plane. So you don't do anything. So theta does it for you. And then when you go off that option in theta would end up with 3 new lattice vectors, which would still give the primitive unit cell. But they would give it in such a way that 2 vectors would be within the plane, and the third vector will be sticking out of plane, of course, somehow, like this. Yeah? Yes. So theta will do it for you. Once you have done that, what you need to do is to choose the number of layers which would represent your surface. Mm-hmm. For that, you need to construct an extension of your surface unit cell corresponding to that number of layers. By the way, at that point, if you do a calculation on the primitive cell, the results will be identical to your previous calculation on the primitive cell. Because this is still a primitive cell.
Yes.
Just with a different choice of primitive vectors.
You're just changing the orientation.
Not orientation. You're changing a region in space, which would be sufficient to reproduce your crystal.
Yes. Okay. Yeah.
So instead of this parallelepiped, you have chosen another parallelepiped, but still it's the same volume. Yeah. Mm-hmm. So okay. So if you don't do anything, you can use this cell for your bulk calculations. That's fine, if you need to. Mm-hmm. Now, so what you need to do, you need now to extend your cell. So you do an extension of the cell. Again, theta has this option, but only along that third vector. You do not touch the surface vectors at all at that point. So you make as many layers as you need to extend it for. In that case, 4. Yeah?
Yep.
So you extended your cell. So now your cell, your primitive cell, would be something like that. It would be little 2 vectors here. And 4 like this. So your cell now, primitive cell, is like that. Yeah?
Yes.
Again, if you start reproducing this cell across, you will reproduce the whole infinite bulk.
Correct.
If you only reproduce this cell in the direction along the surface, so only 2 vectors will be involved, this A1 and A2, but not A3. So this will be your new vector A3, yeah?
Yes.
The big one. That would be the big one. The first 2 are still the small ones. In this case, you will construct a surface. but there will be no gap to its image in the Z direction.
Correct.
So it will be still a bulk, but with this weird asymmetric unit cell.
Yes.
Yes. So in order to construct a proper surface now, what you need to do, you need to separate this out. So these layers need to be separated out. So you will need to choose, instead of vector A3, capital A3, another vector, lattice vector, which would run like this. That would be A3 prime. So this time, what you do, you have already all your atoms which fall within that construction. You don't touch them. There will be as many as you like. In this case, say, if we're talking about, say, silver, one atom in the primitive cell. So in my cell, there will be 4 atoms. And in my file, I would have these 4 atoms in some positions. This time, I choose Cartesian positions. The code would give you these positions, and you can tether, you can save positions either in fractional coordinates or Cartesian coordinates. You will have your Cartesian coordinates for your 4 atoms with the 3 lattice vectors, this one, and this one, which is this. Now, instead of choosing this one vector, you choose this one. It will still keep these atoms there, but this time, if you replicate along A2 and A3, you would go in the direction along the surface. But if you replicate along A3, you will have to replicate in that direction, up and down. And because this vector is large, it will jump.
You create a gap.
The top, up and jump down. There will be a gap between these layers. So you would have your layers, 1, 2, 3, 4, and then another 1, 2, 3, 4 here, another 1, 2, 3, 4 here. Your lattice vector will be that big. Of course, you can make a mistake and make this lattice vector small, in which case your image will be here. Yeah? And you may not want that. You may want to keep this gap big enough so that interaction between this layer, this slab, and this slab be negligible. Yes. So once you constructed this cell, this surface cell, you would choose a gap big enough. And how to choose that big enough gap? You would simply run a calculation as a function of the gap without doing any relaxation. If the gap is too small, you would probably see a difference in the energy when the gap is changed. Maybe small, but maybe significant, depending on the distance. When at some distance, you would find that there's no change of energy anymore. Yeah?
Yeah.
Which means you reach that point after which interaction non-existent.
When you say without any relaxation, you mean like we freeze the atoms?
Freeze the atoms, because at that point we're not interested in atomic positions where they should be. We're interested in finding the gap.
Okay.
Only.
Okay. Okay.
Yeah.
Okay.
And that doesn't matter whether this atom moved by 0.1 angstrom to the left, to the right, or not. It's not of importance.
Okay.
Yeah.
Does that?
So we are trying to construct. You see, we are trying to construct a procedure which would deliver the result as quickly as possible.
Yes. Okay.
Yeah. So this is how we would find the gap. Once we know the gap, we may need a bigger gap if we want to put a molecule inside, but at least we will know the lowest boundary. The gap should be not smaller than, say, 15 angstroms. So that the lattice vector, remember, the lattice vector will be bigger than 15 angstroms because the gap is that distance here. But the lattice vector should go from this atom to that atom. So it should cover the width of the slab as well.
Yes.
But no matter, when you do that calculation, you would deal with full length of the lattice vector, not with the gap length.
Yeah.
Always. Yeah. Anyway, so but just remember, so when you calculate the gap, you should see that there should be enough space to accommodate whatever you would like to put on the surface. And once you put something on the surface, that little thing, that's another image, and that little thing is still there because it's all replicated. You have to make sure that that gap is enough, which would probably be the same or maybe even larger than before.
Yeah. Especially if you put a big thing.
And Tetra allows you doing all this. So Tetra allows you to change this geometry very easily. And I can probably, I don't know if we have time now, maybe we'll do it next time, because we still have to consider K-points something, yeah? It's kind of important. But I think it would be a good idea actually to sit down and construct a bulk, construct a surface of something, yes? With Tetra. Yes.
Maybe you can do this next time, and then I can install Tetra for Connor as well.
Oh, yes, yes. Okay, good idea.
Because Ing has installed, but I don't think Connor has ever seen Tetra.
I definitely don't have Tetra.
Oh.
Yeah. All right. Okay. So what we have done, we constructed the bulk, at least in the virtual world of our mental kind of exercise.
Yeah.
We constructed the bulk. We relaxed the bulk, so we obtained the lattice vectors of the bulk. Mm-hmm. We still haven't talked about the K-point something, but I will talk about this today because it's important.
Okay.
And I will have to explain the basis set. I still haven't done this. Oh dear. So we are talking about geometry only now. So we constructed the bulk. Then from the bulk, we went to the surface.
Yes.
We constructed the surface cell. And then what we want to do, we want to expand that surface cell, primitive surface cell, along the surface plane to be big enough to accommodate whatever we would like to put on there, for instance. Yeah? So this way, we would do the expansion of our surface only for little a1 and little a2.
Yes.
So we'll take a linear combination of them with linear integer coefficients and construct a bigger cell.
Yes.
And we will not touch A3. A3, this one, will be kept.
Sorry, I'm still not sure about that.
Will be kept the same, yeah?
Mm-hmm.
Interesting question.
Could you shut up, please? Actually, it used to be that they replied like, "You're not really polite" or something. They stopped doing this.
Oh, really?
Yes, I don't know.
Probably people were abusing the thing.
The people started abusing them. Yes.
Yeah.
Okay. So this is basically a procedure. I didn't. Okay, so there's a number of points you still need to consider. For instance, how many layers of the surface you would take? 3, 4, or 5, or maybe 10. Which layers of the surface you would keep fixed? Because here you also have a few options. You would like your surface to be good enough for whatever you put on it, a molecule or interface. And for that, you need to make sure that the other layers on the other side of the surface would be as bulk-like as possible. Yes? How would you achieve that? You would probably keep them fixed in the bulk positions. It will only allow surface layers to be relaxed. You have, however, another option to make your surface... just a second. Да. Привет. У меня сейчас как бы лекция с Ноттингемом. Ну, все отвезли, все нормально. От Ники пока ничего не слышно, насколько я понимаю. Ну, давай. Чао-чао. Yes, you can have your slab big enough so you have two models basically for the slab. So let me talk you through this as well. So you have model number 1. You have a certain number of layers. You keep these layers fixed. You may put some hydrogen atoms here, link atoms, to terminate your surface. That you would do if you're modeling a covalent system, as you would do for a cluster. Remember, yeah, to saturate the bonds, and you would allow this to relax, these layers, and then you put something on top. Yeah, that's one model. What is good about that model is that it would allow you to keep the number of layers small. What is bad about this model? The boundary condition here. The same as for the cluster.
Yeah.
You need to have enough layers so that the effect of this boundary condition, bad boundary condition, would not penetrate too much in this region where all the chemistry you're interested in happens. There's another model. Model number 2. You have many more layers. And you have, instead of 1, 2 surfaces. And the idea here is that when you have a surface, the effect of the surface would penetrate maybe 2, maybe 3 layers, but maybe not more. Therefore, if I keep these layers relaxed, the same as these ones, so these 2 surfaces would be surfaces, real surfaces, that region here will be like bulk-like. And if I have enough layers, I can really achieve a very good geometry and electronic structure of that bulk. Of course, it will never be the same, but at least it would be something. And then you put something on top, on one surface. What is the advantage of that? Advantage of that is that you don't have any artificial boundary condition at the lower surface of your slab. You have natural boundary conditions, which is a good thing, maybe. Disadvantage, you need many more layers, so your cell will be bigger. I prefer the first model, to be honest, and I do not like the second model.
You don't like the second model?
Prefer the second one. Huh?
You don't like the second model?
Yeah, I don't like the second one. For some reason, I haven't been using it. Maybe at the very beginning I used it. I don't know. But some people do like this, but I think the preference goes towards the first model. If you look at what people are doing, I think most people use the first model. Yeah.
What happens if? Sorry.
I was just say, is there anything particularly you don't like about the second model compared to the first?
It's bigger. It's much bigger, and also it's a bit tricky. It sometimes needs to be really, really big, like twice as big as the first model. Okay. Remember also that you need to have this vector A3 going, and if your slab is very, very thick, that A3 vector would be very, very long. And as the vector is very long, if you use plane wave basis set, then you will have to use a lot of grid points along that direction. The calculation will be very heavy. Very heavy.
Lev?
Yes.
What happens if you don't put the hydrogens? You just fix the...
Then the problem you have is that you have this artificial surface at the bottom. Mm-hmm. You have to somehow negotiate the effect of that surface. But you want that to be as bulk-like as possible.
Okay.
So if you don't put any hydrogens there will be unsaturated bonds for these electrons on these atoms, and that would somehow penetrate that it's a defect, and that defect would somehow perturb the electronic structure of your slab.
Okay.
If you have many layers, as in the second model, that effect will be somehow dealt with. Okay. Simply by the number of layers, because it would simply somehow negate this effect.
Yeah.
Yeah, but these hydrogens, they help. So in a way, this creates also a perturbation, but maybe that perturbation is weaker than without hydrogens, shall we say, because you are saturated bonds and the electrons are very happy. They play music and sing songs. In the first case, without these hydrogens, they would probably be not very happy. They would like to escape.
Okay. I have another question. So if you have, let's say you have two surfaces, okay, one with 5 layers, the other with 6 layers. What it is that you compare?
Yes, that's the right question you asked now. So how do we choose the number of layers? So let's stick to the first model. So what we would do with the first model? So if we're talking about a metal, we would not use hydrogens. We don't need this. We just make up this surface. So we will create a surface, the procedure I described to you, and say we constructed 4 layers.
Okay.
Yeah, good. Now, imagine what will happen if I now add more and more layers to this surface. As we add more and more layers to this surface, I had 4. Now I started adding layers.
Yeah.
And repeated the calculation. No relaxation, just total energy of that system. Yes? As the number of layers is added, you have more bulk-like layers appearing in between.
Yes.
So at some point, the energy would start changing non-linearly at the beginning, but at some point, it would start changing linearly. Because as you add more and more layers, you can think of this as adding layers not at the bottom, but inserting them inside. So you would be making more and more bulk-like unit cells. Your crystal, your unit cell would consist of these unit cells. These unit cells, let's have them in green. They would be like perturbed by the surface. But these ones here, they will be like bulk-like.
Yes.
And as you insert more and more, it will be bulk-like. So the error you're making, what is called surface energy, the change of the energy as you construct the surface, what the energy loses when you remove atoms above it with which they would normally interact, yes? That error would stay here and here, unchanged. But the total energy of the system will simply increase by the number of bulk unit cells you put in. So, in other words, if you now plot total energy of my cell, of this big cell, as a function of the number of layers I create, initially it will go somehow non-linearly, maybe something like that, or maybe something like that. But that at some point it will go linearly.
Okay.
And that means you started hitting the bulk-like behavior in the middle.
Okay.
Yeah. And that means that any new cell you add, any new layer you add it into your slab would feel like being in the bulk.
Okay.
So probably at that point is a good thickness you achieved. Yeah, so you do have bulk layers already there, which is good because surface layers, then they would feel the right bulk underneath them.
Okay. In your experience, how much is a okay-ish number of layers?
Oh, it depends. I remember what it was. It was.
So for gallium arsenide we did 7. Right?
Yeah. You have to do all these checks, but when we did metals, we didn't go more than 4, I think.
Oh, okay.
Sometimes 6. But there is an example which I can't remember. I was actually course of that paper, but I can't remember now. What was the system? Germanium. Maybe it was germanium. Yes, it was germanium instead of silicon. Yes.
Okay.
11 layers.
Wow. Okay.
The guy who did the calculations claimed that he needed to go to 11 in order to have convergence with the number of layers. So what you can do now, when you do the calculation, say you have a metal, so you have two surfaces. Mm-hmm. You don't do okay, if we stick with this model, you have one surface. So you would keep these layers bulk-like positions. So you would not relax them. You would only relax these upper layers. And you would plot the total energy as a function of the number of layers, this kind of thing. Mm-hmm. Yeah? And you would have the same effect. But here you have two surfaces, two different surfaces. Because one surface is not relaxed. Another surface is relaxed. Or if you put hydrogens, then it's obvious it's another surface.
Yeah.
There is a way to calculate the surface energy still. But for that to do, you need to do a little number of tricks. So, for instance, one possibility is to construct your surface, terminate hydrogens both surfaces, then started to adding more layers and expanding that thing, and then taking the total energy of the whole system minus the energy of the bulk cells minus the energy of the number of cells you have and divided by 2. That would give you the energy difference with respect to the bulk. That's the surface energy. And that would be the surface energy with hydrogens in. Now you do this model, and you do the same calculation, and that calculation would give you, so if you have n cells, so 1, 2, 3, 4, 5, 6. 6 cells in this case, yes? So the total energy will be n times bulk energy plus surface energy 1 plus surface energy 2. Surface energy 2. One is associated with this termination, another is associated with this termination. That termination we have already found from that previous calculation, which is auxiliary calculation we need to do. Yeah? So you can work out this, and this quantity can be measured and can be compared. And in fact, you need to achieve convergence of that quantity, the surface energy, with respect to the number of layers. So if you plot this as a function of n, it should go to a Plato. When you reach this Plato, that means we have enough number of layers. Guys, I have a tutorial in 15 minutes. I suggest we stop here, but we haven't considered quite a number of things. So for the next time, what we need to consider, let's just remind ourselves, K-point sampling and basis set. We haven't done this at all. Yeah? And then tether, maybe, if we have time. Yeah, so what we have just done, we looked at the geometry. So basically, yeah, look at the geometry. Direct lattice, how to construct lattice vectors in the direct lattice. There's a choice of doing this. You can also construct large unit cell or supercell as well, yes, by taking linear combinations of these lattice vectors with integer coefficients. We have made an exercise how to get from the primitive FCC to the crystallographic FCC, which is not FCC, which is simple cubic actually, of the smallest possible volume. And we worked out reciprocal lattice vectors for that lattice and for the simple cubic lattice crystallographic cell. And I gave you an idea how to construct a surface, just geometrically from Miller indices. Yes, how we build a slab by replicating along the third direction, which is not within the surface, sticking out of the surface. We construct, and we discussed a little bit how to optimize these things, but we cannot do everything at once. So let's try. So when shall we do it next time?
Whenever you're ready. When you have time.
So
we'll make it work.
Yes. I have Thursday. What about Thursday? Shall we do Thursday?
I'm okay with Thursday.
Yeah, Thursday's fine with me.
Is that okay with you, Ian?
Let me see.
Yes.
It copied, and I accept. I'm not sure what will happen if we have this link now. Philip, did you have a link?
I don't know. I think I have the link, but I don't. I don't know.
So let me see what will happen now. So
I just copied this. Let me see.
I just copied that. Does it mean that you would get automatically a message that there's a new something?
I don't know. I'm refreshing now to see if something happens.
And let me send you this link anyway.
Okay.
But it should be the same link as today. We can keep the same link, yeah? 10 o'clock on Thursday. Yeah, is it okay?
Yeah.
Okay.
Otherwise, I can create a proper link again. But
that's fine.
You should be okay. So
Okay.
I'm stopping the recording.